Okay, in this example, we're going to simplify the expression 4 times the complex number 2 plus 3i times the complex number 4 minus I. To do this, since there are three things being multiplied together, we need to approach the problem the same way you would approach 2 times 3 times 4. In 2 times 3 times 4, you would group 2 times 3 together and get 6. And then take that result and multiply by 4, giving us 24. In the same situation here, we have to group two of these together first and multiply those, and then take that result and multiply it by the third. So I'm going to distribute 4 through. 4 times 2 is 8. 4 times 3i is 12i. So there's the result of that first multiplication. I'll bring my 4 minus I down. Now we just have to do the second multiplication and then combine any like terms. So 8 times 4 is 32. 8 times negative I is negative 8i. Remember, since it's a binomial times binomial, we have to do the full distribution here. 12i times 4 is 48i. And 12i times negative I is negative 12i squared. From here, remember, you can either combine like terms, but I recommend dealing with the I squared first so you don't forget about it, because on like x, I squared means something and represents something. Therefore, we replace I squared with what it means. I squared is negative 1. So this is really negative 12 times negative 1, or positive 12. I'll bring everything else down. Now I do know I could have combined these like terms during that stage. However, I usually wait until after I completely change the I squared, because oftentimes I found that people will forget to go back and combine these two if they combine the i's right away. So I usually wait until after I deal with the I squared first and then combine like terms all at once. So 32 plus 12 is 44. And then negative 8i plus 48i is positive 40i. And there we have it. Okay, in this video, we're going to talk about the complex conjugate. The complex conjugate is where two complex numbers with equivalent real parts but opposite complex parts. That's what they are. They're basically two numbers that have the same real part but opposite complex parts. Their product actually happens to be a real number. I'm going to give some examples here in a second. So if I look at a simple complex number, 4 minus 3i, the complex conjugate would be keeping the same real part, but changing the sign with the imaginary part. If I could write the correct number, there we go. Those two are complex conjugates. We have 4 plus 3i and 4 minus 3i are complex conjugates. Similarly, negative 2 plus 7i and negative 2 minus 7i are complex conjugates. They have the same real part, but different complex parts. And just some weird special cases that could happen, one which is kind of pointless to talk about. I'll start with the kind of pointless one. 5. What's the complex conjugate of 5? Weirdly enough, remember 5 is 5 plus 0i as a complex number. So the conjugate of 5 plus 0i would be 5 minus 0i, meaning the complex conjugate of 5, because that's what this is 5. Pretty much completely pointless to talk about. Now, the one that's not pointless to talk about is probably the other special case where we have 2i, for example. As a complex number, 2i, it would be written as 0 plus 2i. Therefore, the complex conjugate of it would be 0 minus 2i. So if it's just the imaginary part that we have, the conjugate would just be changing the sign. So those are all examples of complex conjugates, and as well as the two kind of funny cases where you only have the one term. But let's talk for a second now about what this part here means. Product is a real number. So I'm just going to use that first one I wrote up as my example, and we'll take a look at that real quick. 4 minus 3i times 4 plus 3i. So if I distribute this out like normal, 4 times 4, 16. 4 times 3i is 12i. Negative 3i times 4 is negative 12i. Negative 3i times positive 3i is negative 9i squared. Now, if you are multiplying by the conjugates, the 12i and the negative 12i, the middle two terms should always cancel out. If they're not canceling out, something went wrong. And in fact, you can actually use this as a shortcut. When you multiply conjugates, all you really have to multiply is the first times the first and the last times the last, because the middle terms will cancel out. I often don't do this at the board whenever I teach because some people don't understand or don't ever remember that you can't always do that. That only works when you're multiplying conjugates. But if you can remember that, awesome. Use it as a shortcut way to help yourself. Once you have that, we're going to go ahead and deal with the next part. And that part deals with the I squared. I squared, remember, means negative 1. So the middle two terms cancel out. Cool. I squared is replaced by negative 1. So negative 9 times negative 1 is positive 9, giving us 16 plus 9, which is 25. Now, the product being a real number means that no matter what combination or what complex number you choose, when you multiply by its conjugate, you're going to get a real number or a number without the I part in it. So no matter what combination, when you multiply complex conjugates, you're always going to get a real number, and the i's will all cancel out. And that's everything about conjugates. In this example, we're asked to write the quotient 8 divided by the difference of 4 and 3i as in a plus bi form. This is basically division of complex numbers, and you may also see it referred to as simplify. To simplify a division of complex numbers, it's defined a little differently than normal division. It's defined by getting rid of the I out of the bottom or the denominator of the fraction. That's how we define simplifying or dividing complex numbers here. So how do we actually go about doing that? Well, that's where that vocab word that we just looked at comes in handy. The complex conjugate. When you multiply by a conjugate, it cancels out the imaginary part and you're just left with a real number, which would mean that real number does not have an I in it. So the way we approach this is we're going to multiply by the conjugate of the bottom so we can get rid of the i's in the bottom. Now you might be thinking, why am I putting the fraction here? Or, wait, I can just multiply by whatever I want? Well, no, I can't just multiply by the conjugate because I want to multiply by the conjugate. I need something to balance it out. So what I'm going to do here is I'm going to multiply the top and bottom of this fraction by the conjugate of the bottom. Okay? And what that is doing is it's essentially multiplying by 1. If I think about 5 times 3 over 3, if I just decide to multiply 5 by 3 over 3, well, this is 1, and 5 times 1 doesn't actually change the value. It might change what it looks like until we reduce, but it doesn't change the value of the number. Because we're multiplying by 4 plus 3i over 4 plus 3i, it's essentially multiplying by 1, which doesn't change the value of this expression. It might just change what it looks like. And again, remember, it has to be the conjugate with the sign being the opposite in the middle. Okay, so let's go ahead and do the multiplication. On top, when you multiply fractions, just multiply across the top. So because there's 2 terms in the second fraction, we're going to have to distribute. 8 times 4 is 32. And 8 times 3i is 24i. On the bottom, we're going to have to do that as well. But because they're both binomials, we're going to have to do that full distribution, the whole FOIL method. 4 times 4 being 16. 4 times 3i is 12i. Negative 3i times 4 is negative 12i. And negative 3i times positive 3i is negative 9i squared. Again, remember that since the bottoms are conjugates of each other, those middle terms can cancel out, and you can actually use the shortcut I mentioned previously. The top you would try to simplify, but nothing can be combined up top, and there's no I squareds. So in the numerator, we're going to be left with 32 plus 24i. I can't do anything with that right now. On the bottom, remember I squared means something, so we have 16 minus 9 times negative 1. Negative 9 times negative 1 is positive 9. So in the bottom, we really have 16 plus 9, which is 25. Sometimes there's a number of ways you can write the answers, depending on the situation or what the question's asking for. This one's specifically asking for a plus bi form. So I'll elaborate on that in just a second. But sometimes you can reduce this fraction at this stage. In order to reduce it, something has to go into this number, and this number all at the same time. Nothing in this case does. But to represent an a plus bi form, we have to go one step further. And instead of dividing both terms by 25, we have to write it as 32 divided by 25 plus 24 divided by 25 I. Putting the I off to the side. Having the I off to the side or on top is equivalent. Having it in the bottom would actually result in a different value. So please be careful that the I is not in the bottom. Should be off to the side or on top, but both would be equivalent in this situation. You can look up properties with fractions and stuff to kind of see a little bit more in depth with that. But you should try to reduce the fractions if possible. Neither one can reduce here. So this is the answer in a plus bi form.